All right, the last three terms, again, you've heard, you've seen, you probably tried to forget, you're one of the ones that hate stat. But I want to bring them up again very quickly just because this is what we're doing. And I want you to see why we do this. My goal for the end of this little rant that I'm going to go on is explain to you why we do some of these things. So very quickly, I'm going to talk through what a normal curve is, and I need that to explain the other two, which is a p-value, and then something called a null hypothesis, which I mentioned briefly, but I didn't make a big deal of it, so let's just talk through these things really quick. All right, I'm going to show you a pretty picture of a normal curve before I start drawing, because I can't draw at all. But nonetheless, here are some pretty pictures of a normal curve. Remember back to statistics, your teacher would draw these curves on the board, they would draw some random lines, and they'd tell you, hey, this middle line means something, and then if you go one unit away, you go another unit away, and you were probably like, at that point, I wonder what I'm going to have for lunch, all right, instead of actually paying attention. But let's try to remember what the teacher was saying for just a second. So when they drew this curve, they always drew a big hump in the middle. The middle line always meant something. Here they have it labeled as X, so hopefully that'll tip you off. This is not just any old ordinary X, it's a symbol for a word. So what was this middle line representing? What mathematical word?
Mean.
The mean, the average. All right, so what this graph overall is showing you, right, is how many people will get a score of something on some test. That was pretty vague, huh? Your teacher probably used intelligence as one of the examples. That's the pretty standard one that we teach because the mean intelligence level is 100. It's just a nice, pretty number, right? What that basically meant was, if I measured everybody possible, ever, right, and plotted out all of their scores, I would get a curve that looks like this, because most people are going to score what this average number is. Right? That's why there's a taller hump here in the curve. That means more people are scoring that number. There's a smaller hump over here, because this means I'm getting further away from that mean, or I'm getting a bigger and bigger and bigger number. In the case of IQ, that would be a higher and higher and higher IQ. And there's just not going to be as many people with that high IQ. Same thing on the other end. As I'm getting further and further away from that average IQ score down here, which would mean a low IQ score, there's just not very many people that get that low IQ score either. So in general, does this kind of weird chart make sense? Again, it's giving you average scores of something, because again, most people would score roughly whatever the average number is, which is what the middle represents here, and fewer people are going to score the extremes. Yes? Okay, a few more things. Here's another pretty chart here with a few more weird mathematical symbols on it. So here's another symbol for the mean here. Again, the middle line's always the mean. Now it shows you the mean plus this other weird symbol, which stands for standard deviation. And then a mean minus a standard deviation, minus 2 standard deviations, plus 2 standard deviations. That's how we decided where to draw these other lines. What that basically means is, in another mathematical way, the average that people would score, the average plus the first typical amount of variance. If I added 2 amounts of that variance, 3 amounts of that variance, again, don't need to remember all that, but it's going to relate to some of the things that you are testing later. Because the reason I'm showing you this, and I got one more picture for you, that there are very mathematical computations of how many people will fall within these ranges. So if I was to take the average scores for all the people, let's do IQ again. The average IQ score, again, was right here in the middle. All right? If I went to 1 standard deviation above the normal IQ and 1 standard deviation below, and I looked at how many people would fall, either one below or one above, it would be about 68% of the people. And it doesn't even matter what trait you're talking about. This 68 is a very standard math number, so I could be talking shoe size. Here's the average shoe size, 1 standard deviation above, 1 standard deviation below. 68% of the people would have that range of shoe sizes. Most people don't have a size 20 shoe. Most people don't have a size 2 shoe, right? Standard mathematical numbers. If you go one more deviation out, you get to 95%. So most people are going to be within 2 standard deviations. In other words, really, people don't ever typically get to those extremes, that size 20, that size 2. In fact, right, beyond the 3 standard deviations is only 1% of the people. That's how rare it typically is. Okay, hold those thoughts a second. I'm going to make that make a tiny bit more sense, but I'm going to switch gears before I come. Let me talk a few things again. Switching gears. Go back to that chart. If you were to play a game of dice, I'll say you just have one die, right? You would win the game if you rolled a 3. What are the chances that you win? You get one roll. What are the chances that you're going to win?
1 out of 6.
How did you get that? How did you get 1 out of 6?
Because there's 6 number on one die.
Perfect. All right, there's 6 numbers on one die, but there's only one of the number 3. All right, so to win this game, I'd have a 1 out of 6 chance. Does that make sense? What kind of math was that we just did? Probability. There's somebody that remembers that word. Probability. All right. When you were doing probability, what were you calculating? What is this 1/6 number? Put it in just general terms, in unmathematical terms. To do that, let's do this. What is 1/6 as a decimal? In case you don't feel like calculating it out, it's roughly 0.167. How do you make 1/67 a percent? Just move the decimal a couple places, and you get 16.7%. Okay, so now put it in general terms. If I have to get a 3 to win, how likely am I to win? What's the word you would usually put after that? Starts with a CH. Chance. There's a 16.7% chance that I'll win. Does that make sense? Right, that's not really math, that's just a game, right? That's your Vegas odds. 16.7% chance that was the easiest Vegas game ever. Okay. Now I want you to switch gears back, and I'm going to come back to this. Somewhere in your life, hopefully in stats, but definitely by methods 1, I know I've said it in here already, you were told that you wanted to set your alpha level to 0.05. Somebody probably told you that alpha is the amount of error, and yeah, you're like, yeah, that doesn't mean anything to me. All right, that's okay. I don't care if it still doesn't mean anything to you. But I want to talk about why we use this special 0.05 number. Why you also would write your p-value needed to be, wrong way, less than 0.05. That's greater than. Can't talk out loud. Less than 0.05. Why did we say that? All right. Now, here's how I'm going to make it all come full circle. Let's go back here. Let me draw this again. What I mean by I can't really draw. Mine aren't as pretty. We always said the mean was in the middle. I use that symbol for the means, population mean. And what we said was this. Here's 1 standard deviation away. Here's 2. Here's 3. 1 standard deviation, 2 standard deviations, 3 standard deviations. We said that we know, right, that between, here's the 2, so minus 2 plus 2 standard deviations. And again, that's the fancy population standard deviation symbol. In here, right, is 95% of the people will fall in that range. Right, so how many people is left? How many people would be left at the 2 ends, even though I didn't quite draw it to scale? If 95% fall in here, how many people are on the outside? 5%. Okay, hold that thought just a second. Go back over here, this magical number that I told you. Turn it into a percent for me. Just like you did up here.
5%.
Aha! Right. That's when we get that magical 5% number. Right. It wasn't just a random thing we picked. We said we want it to be, we will consider it to be extreme if it's on one of the 2 ends, if it makes up that outer 5%. And then we just changed it to a decimal instead of a percent and said 0.05. Okay, one more thing to keep making this come around. All right, this semester, we've been writing our hypothesis, and I'll tell you what the A means in just a second. We've been writing, we predict that our... I have to stand crooked. We predict that our IB will affect our DB. All right, remember that's how we've been writing it? No matter what your IB and DB were, that was the form I told you to use, just so it was pretty clear. Okay, what this really means, what we really are curious about, is this question. are my IB groups different? Do you agree? That's kind of conceptually what we're curious about. All right, so I've used this IB to split people into groups, and then I'm seeing within those groups, did they have different scores for people? So like if I split people into different age groups, did they have different life satisfaction scores? If I split people into age groups, did they have different self-esteem scores? Split people into socioeconomic groups, did they have different driving anger scores? Does all that make sense? Just that piece, just that little piece. Okay. What we really want to know, again, mathematically, is are these groups different? Is there some way we can test that? And without going into too much math, because it would blow your brain for right now, and it took multiple semesters for me to be taught it. Right? Just believe me when I say this statement. You cannot mathematically test if two things are different. Right? Again, there's a whole lot of formulas and stuff that goes into that, but believe me when I say that. But what you can test mathematically, right, is what is the chance that two or more things are the same. It sounds simple when you just say it in English, but believe it or not, mathematically it's a lot more complicated. This, we can test. What is the chance that these two things are the same, or that these three things are the same? Well, for us, what we care about, these things, are the independent variable groups. What is the chance that my independent variable groups are the same? Still following me? Everybody with me? Okay. Because of that, mathematically, we are testing something that we call a null hypothesis. It's related to the one we've been writing, which now I'm going to give a name, called the alternative. Some people may call it something different, but this is the name I like to use, because then I get to call it the HA. The HO, right, is actually like a nothing. That's null. That's why we put an O there. And basically what it is the opposite of what we said up here. Right? So basically the IV will not, that's the easiest way to write it, affect the DV. Put that in easier terms that aren't mathy sounding, my groups are not different. That's what we are testing mathematically. What's the chance that our groups are not different? All right? Or what are the chance that my groups are the same? To use a non-double negative there, English-wise. Okay. Here I go. Stay with me. I know I've been throwing math at you. Don't blaze over yet. Here's the part where I make it make sense. Okay. What you test when you run a t-test, or an ANOVA, or a two-way ANOVA, or even a z-test, or even a correlation for that matter, when you get it to spit out at you a p-value. Remember when we looked on that SPSS output, we looked for that p-value, and we compared it back to this 0.05? And I said, don't worry about it yet, but if it's less than that 0.05, you know that your groups are significantly different. If it's greater than that, they're not significantly different. What I was basically having you do is to look at the chance, related to this null hypothesis, that your groups were the same. All right? If your p-value equals 0.65, which again is much greater than 0.05, that means there's a 65% chance that your groups are the same. So they're probably not different. But if your p-value is 0.03, which is less than 0.05, that means there's a 3% chance that your groups are the same. That probably means that they're different. Does that logic kind of make sense? That's all you're doing. That's everything that they tried to teach you in stats and everything. That's it. That's why you compare it back to the 0.05. That's why you have these weird normal curves that your teacher made you draw. What you're saying is, when I have these groups, right, what's the chance that they're different? What's the chance that they're the same? All right, so the terms that I wanted you to know. You know independent variable now. You know dependent variable now. You know extraneous variable now. I don't really care if you can describe a normal curve, but just know that all that testing you're doing, you're using the principles of the normal curve. So when you have the computer run a t-test, when you have the computer run an ANOVA, when you have the computer run anything, the reason it can do that is because mathematically it's using the principles of a normal curve. We set our p-value at 0.05. We decided to use that 2 standard deviation thing and only use the 2 extreme ends, which made up 5%. I could have gone one more and done my p has to be less than 0.01, which is even more extreme. But the standard acceptable use in most sciences is the 0.05. It's 2 standard deviations away. And then now you understand what the null hypothesis is. Even though you won't write about it in your final paper, the only place you're going to use it is in this homework assignment tonight. Mathematically, that's really what you're testing. And again, hopefully you get to reject the hoe, meaning your groups are different, which is originally what you had hypothesized. I hypothesized that my independent variable did affect my dependent variable, meaning my groups turned out different. Did I come back around enough of a circle? Even though you're not going to be a stats expert, you sort of understand a little more why your teacher made you talk about all those things. That was my goal.